Yeah, in this meeting, our topic is about variable and random variables and also their function. Uh, that we start with the motivation about the random variable. Consider our previous experiment, that is, we are tossing an fair coin, and then we want to find the probability of the event that KH shows up. Uh, in this experiment, of course, our sample space is not a number, right? It is an array, or array like this, or age. Then for example, ht and the rest are age and so on. Yeah. If we see our outcome is not a number, but in our analysis, we need to have a number for doing our mathematical analysis or our modeling. So the idea is we correspond each element of the sample space into a real number. For example, we put this outcome to a real number L1 and this outcome to L2. Yeah, and this idea is called the random variable. That is a function. Actually, a random variable x is a function from the sample space S to the set of all real numbers R. If I write in the notation of the function, we can write x is like this, S from the sample space to R, which correspond every element in S, let's say omega, to a unique number R. Then we can write with this notation. Yeah, and then for the illustration for the random variable, if we have S for the sample space and an element omega, we correspond this omega into the real number x omega. If we have another element, for example omega 1, it is correspond to another number omega 1, and because the random variable is a function, it is possible to correspond omega 2 to this number, because x is a function. Yeah. So in conclusion, the random variable is a method to quantify our outcomes. Yeah, and we can do it for every sample space, whether it is already a number or it is not a number. Okay. Yeah. Let's discuss some examples. Oh yeah, I'm sorry. Before go to the examples, for the remark, it is important to know all members of S, because we must define the explicit formula for the function, and then it is a notion that is all possible values of R is called the values of X, and we will write this X. R is an element of X. Okay, let's discuss the first example, that is the experiment of tossing two fair coins. From the previous meeting, we have learned the sample space is this, consists of 4 elements, and then I define random variable x as the total of outcomes of h. After that, we have to find the formula of the function. Yeah. From the definition, x is a function from S to F. And then after that, we correspond all elements of S into a real number. Yeah. For example, HH, we will correspond it into a real number. What number is it for HH? Could someone help me to write this number?
2 maybe.
2? Right. Right one. H is H corresponds to 2 because we have 2 heads here, right? And Owen, could you continue your answer for the next
1.
1, and then
The next one is 1 as well, and the last is 0.
0, right? Thank you, Owen. Yeah, it corresponds to 1 because there is only one H, and similar for this element, and for the last element, because we don't have H, we correspond it to 0. Okay, and then yeah, we have done with this function with the formula, and then we deal with the set of all possible values. What is the set of possible values? The set of all values of x. What is that set? All possible real number r, which correspond to this function. The set of possible values. What is that?
Is it 0, 1, and 2?
0, 1, and 2. Right. Thank you. The set is 0, 1, 2. It is enough to list all possible numbers here. Okay, thank you. The set of values is this set. After that, since the coins are fair, we can compute all the possible probabilities. That is the probabilities of the head. They are the probabilities. The head is 0 for this notation. There is no heads, right? We can use the notion of the random variable to simplify our notation about the probability. So this notation p x equal to 0 is correspond to the probability that there is no x here. And then this notation, oh yeah, of course the value is 1/4, right? And the notation p x equal to 1 is correspond to the number of h is 1. Yeah, and so on. For 2 means the probability that there are 2 heads. Yeah, and so on. Yeah. And as I mentioned before, we quantify all the outcomes to a real number. Since the sample space is not a number, right? But after we define a random variable, we get some numbers, and then we can do another analysis. Okay, great. That we go to the second example. That is the experiment of rolling 2 fair dice, and for this they are four-sided. Of course, the sample space is S, and then I define a random variable X that denotes the sum of two outcomes. Then we will see what is the formula of this function. Could someone answer the formula for each pair A and B? Sum of two outcomes. That is the random variable. Yeah, this is the keyword, the sum of two outcomes.
Is it from 2 to 8, sir?
Before we go to the set, we must define what is the formula of this function.
Is it A plus B?
A plus B, right? And your answer for this set is all possible values, isn't it? Possible for all values. Is that right? Right. You mean this is for the set of all values? Yes. Yeah. All right. This is the set of all values of x. That is all possible real number 2 until 8. Yeah, because our possible value of a plus b are only 2, 3 until 8. Okay. Okay. Thank you, Said, for your answer. Is there any question from another student? Okay, yeah, I think it is it's an easy example. Okay, let's move to our next slide and next example. Yeah, I'm sorry, this is mistake here, typo. We deal with the six-sided dice. We throw it 2 times, and then we define x, the random variable, as the sum of two outcomes. Yeah, I think it is similar with the previous example, right? Our formula is a plus b, and then our set of all values. What is this set? Set of all values. Set of all values of the random variable.
1 until 12, 2 until 12, I guess.
2 until 12, right? Yeah, these are the possible values of a plus b. Okay, thank you. And then we move to the next example, that is the experiment of tossing a coin until a head comes up. From the previous meeting, we have known that the sample space is this S with the elements H, TH, TTH, and so on. After that, we define a random variable X, which denotes the sum of tosses until a head comes up. Yeah. The sum of tosses. How many tosses until we get a head? Okay, this is the definition of the random variable. After that, we will construct the formula of each element. For example, h, th, tth, and yeah. What is the number which corresponds to h?
1.
1, right? Yeah, because we have only one toss, right? And then for th,
2.
2, tth,
3.
3. Okay, yeah, and we will continue it until non-infinite. We do it infinitely, and yeah, for this case, it is enough to write the general form of the function, that is x t t th for n minus 1 t and 1 h. It is n. If we deal with this infinite case, we need to write to the general formula like this. It is enough to describe this general case. Okay, and we continue. What is the set of possible values? Set of all possible values. What is that?
1 until infinity.
1 until infinity. Yeah, right. There are the elements are 1, 2, 3 until n, and yeah, so until infinite. Right? Yeah. Okay, great. Thank you, Awan. Is there any question from you? Okay. Until now, we have two general case. That is the sample space, which is finite, as the previous example, and then this sample space that is infinite, but we can correspond this set with the natural number. Yeah. Okay. Let's move to the next example. Yeah, we back again to this example, that is measuring the lifetime of a battery. But it is different with the previous example. That is, in this case, we are interested only on these two condition, whether or not the battery lasts at least 2 years. Yeah. In this case, we do not deal with the actual lifetime, but we have to answer: is it could it live for 2 or more years or not, like that. So we can define a random variable like this. That is, ix is 1 if the lifetime of the battery is at least 2 years. And then we give the value 0 for another situation, or yeah, in this case, for before 2 years, right? Less than 2 years. Yeah. Okay. This is the last example for our random variable. Any question until now? Okay, good. Okay, we will continue our discussion into the the big classification, the two classification of the random variable that are discrete and also continuous. Let me start with the discrete. The discrete random variable is a random variable which has the set of all values is a finite set or a countable set. Finite means there are finitely many elements, right? And for countable, it is a set. It is a set like this: x1, x2, xn until blah blah blah. And if we can write the index with the natural number, we call this set as a countable set. Countable can be infinite or finite. So a random variable which the set of all values is finite or countable is called a discrete random variable. This is this is one of the classification of the random variable. And then of course, because we also deal with the probability, with we also define a function that correspond all values of x to the probability, to its probability. We call this function the probability mass function, or PMF, of a discrete random variable x. F is a function from x to the set of all real numbers r, which corresponds x to its probability, to the probability of x is equal to little x, and we call it the PMF of a discrete function. After that, we also define the cumulative distribution function, or the CDF, which denote by big F of a discrete random variable with PMF little f. And then the definition is like this: fx is equal to the probability of x less than or equal little x, or the sigma of fy for all y less than or equal x. And then this function is defined on all real numbers, so we must find this function for all x. It is the CDF is different with the PMF, because in CDF we must find all the fx for x in real, but in PMF we only need to find the value of fx for every x in x. Okay. This is the definition about PMF and CDF. Let me move to the practical example. I'm sorry. Before we go to that example, there's a method to prove a function is a PMF. That is, we need to check that the value of fx is greater than or equal 0 for every x, and the sum of all fx for x in x is equal to 1. This is a requirement of a function to be a PMF. And yeah, we consider this example. Yeah, as we discussed before, this is the definition about the random variable, and then this is the probability of this value of. Consider again our definition of in PMF, that is the probability of x is equal to little x. Yeah. From our definition, obviously the value of p x equal 0 is equal to f0. Yeah, just right based on the definition, and this is for f1 and this is for f2, and we have done with these three probabilities. Therefore, the PMF of the previous example is given by this formula. F0 is equal to 1 over 4, F1 is equal to a half, F2 is equal to 1 over 4, and Fx is 0 for another x. And if we check the two requirements, the sum of all Fx, where x from 0 to 2 is 1, we sum up these three numbers, and then the value of Fx is greater than 0, right? Greater than or 0, greater than or equal 0, right? From the definition. Yeah, after that, we will compute the CDF of this PMF. So let's we move to the whiteboard. Okay, I will draw the illustration about this. This is for 0, 1, and 2. 0 corresponds to this value, 0 to this value, and 2 to this value. Okay, and Fx is 0 for x not equal to for x not equal 0, 1, and 2. Let's find the CDF. Because it is discrete, we will use the sigma of Fy for all y less than or equal x. This. Yeah, and of course, because it is a CDF, we must find the Fx for all x in the real line. Yeah. For the CDF, we have to divide the real lines into some cases. That I give brown color to the area less than 0, and then green for this area, orange for this area, and yeah, maybe pink for this area. We will find the CDF for at least 4 cases. Yeah, let me start with the first case. That is the case x is less than 0. And yeah, we will find the value of Fx. From the definition, it is equal to the sigma of Fy for y less than or equal x. And from our case, x is less than 0. What is the value of this Fx? We sum all Fy for y less than 0. What is the value of fy where y is less than 0 from the definition of the PM? From the illustration, we see that the value of f0 is 1/4, f1 is a half, and f2 is 1/4. And yeah, we have this sigma fy y less than 0. Could someone give the value of this function? Yeah, from the could someone help me for this value, please?
0, sir, maybe?
0. Yeah, right, 0. Because could you explain this, Owen? Why we get 0?
Because the x is less than 0 and 3.
Nah. Yeah, right. Y is less than 0, right? And we see
Yes.
from the definition that fx is 0 for x not 1, 2, and 0, right? Could you continue for the next area, the green area?
The one is a quarter.
A quarter, right?
1/4, yeah.
1/4, because the only non-zero value on the left of 1 is only this point, right? Yeah,
Yes.
this is 1/4, and then for the orange area,
3/4.
3/4. Why can what is the reason of this?
Because you just add the 1/4 and 1/2.
Nah, right. Because the value of x is less than 2, and the non-zero value of f, which is less than 2, is f0 and f1. So we sum these two numbers and we get 3/4. And then now for the last, the pink area, x greater than 2, what is the value of fx?
1.
1. Yeah, right. 1. Its value is 1. Yeah, and we have done for our 4 cases, and we still have three case, that is for x0, x1, and x2. What is the value of the CDF in 0? F0, consider that our CDF is used greater than or equal, less than or equal. I'm sorry. So for f0, y less than or equal 0. What is the value of f0? This is equal to f0, right? And only f0, because the y which fulfill this condition is only y 0. So it is a quarter, and then with the similarization, the value of f1 is this, and the value of f2 is 1. Yeah, we finish all cases, and then we can find the value of the cumulative function. Yeah, and for our simplicity, we can write the final answer as this function. Yeah, here is some spaces. We can write it in the simple formula. 0 for x less than 0, a quarter for x from 0 less than or equal x less than 1. So this for this, and 1 for x greater than or equal to. Yeah, this is the final answer of our CDF. Any question from you, please?
So, I still don't understand the difference between the x and y. Can you explain it again?
Pardon me, please. What part you don't understand?
The difference between variable x and y, sir.
Oh, x and y. Okay. Yeah, I will highlight this formula. Yeah, sorry. To start it, yeah. Actually, for the x is the from the definition of CDF, we know that the CDF is a function from R to R. So we want to assign all x to the value of fx. For actually there are real number, but in our practical, the y we use all y in x. So we only consider all y in x. That is the set values of the x. That actually we have the complete formula like this: all y less than or equal x, and y is an element of x, like that. How about this explanation side?
Okay, sir. Thank you.
Yeah. I hope you can receive this explanation and idea. Okay. Other questions? Great. Yeah, let me continue to the next slide. Yeah. Yeah. Okay, we will discuss this problem. We have the probability mass function as this formula, and then we must find the CDF. Yeah, I will give you a couple of minutes to do this problem. Please find the CDF, that is the that. Okay, I think time is up. What is the definition of the CDF? Could someone help me to write the values? Okay, what is the definition of the fx? Okay. Okay, maybe I will give you some hints. We divide our real line into some areas. For the first area is x less than 1. After that, this area and this. Okay, for the first area, what is the value of the fx?
0.
0, right? 0, because we don't have the y that is less than 1, right? Less than x. Okay. After that, what is the value of this area?
Half.
Half, yes. And then this
5/6.
5/6. We sum half with 1/3, and then for the last, what is the value?
1 divided by 6. No, wait. 1.
No,
Yeah.
1, right? We sum these three numbers. Okay. Yeah. Thank you, Owen, for your answer. Is there any question from another student?
Sir, can you explain how why is it sum of all three possibilities?
Why we get these three areas?
Yes.
Oh, why? Oh, yeah. The idea is like this. First, we draw the real line and then put all values of x, 1, 2, and 3. After that, yeah, for our cases, we want to divide this real line effectively. So the most effective way to divide it is by this. You find, first of all, we search the first value, the lowest value, like for example 1 in this case, and then yeah, you only to write this area to the first, for the first area. After that, after we meet this value, we search again the next value, that is 2. Yeah, after that we use this area for the second area, and then after that we search again the next value, that is 3, and then use the third area with this area. And then the rest part of the real line, of course, this area. So this is the fourth area. Yeah, this is the idea to divide the real lines into 4 cases, and we can get the value of CDF. Okay, right? Could you receive this idea?
My question is actually, why is it x when x more than 3 is half plus 1 divided by 3
Oh,
plus 1
oh
divided
my
by 6?
God. I'm sorry. For the last cases, yeah, I will give you an illustration. This value, maybe we see for the cases x greater than 3. After that we see for 3. If x is greater than 3, from the picture we can write x like this. X is greater than 3. After that, by the summation formula, fy, y less than equal x, y in x. We see see all values of x that less than x. Of course, the non-zero values are in this place, this point, and this point. That's why we get these three summation type.
Okay, sir. Thank you. Thank you.
Yeah. Just illustrate it with the real line. And then for the case x equal to 3, yeah, you can see that we add this point, and also this point. Okay. As I said, thank you for your question. And I'm sorry, I misinterpreted your question before. Another questions?
Sir, I have a question.
Yes, it is. Please.
Why is there no x equal to 1? Is it because the first function is half?
X2 equal to 1.
Yeah, why is there no x equal to 1? There's x less than 1 and then x between 1 and 2, but
Oh yeah, it is just the different return of the definition. Actually, the case x equal to 1 is accommodated by this interval.
I don't know. I mean, why is there no x equal or less than 1? Like,
Oh, x.
yeah, that.
Oh. Oh, if we write, I'm sorry, I will use another color. If we write x less than or equal 1, there are contradiction with the second. There are contradictions in an interval. In the first interval, the value of x equal to 1 is 0, but in the second interval, the value of x when x is 1 is a half. Okay.
Okay, sir.
Okay. Yeah. So be careful for our area. Okay. Okay. Next discussion for this problem. Okay. Let's move to the next example. Yeah. Because of the time and the previous experience in another class, which could not give the complete answer for this exercise. I will leave this exercise for you, and we continue to the continuous case. Yeah, and also if you want to see another problem, you can do this exercise. Okay, this is the end of our discussion about discrete random variable. And then now we go to the continuous case. Okay, the motivation is like this example. A man usually goes to his office by a bus, and the bus arrives every 5 minutes. And then we define a random variable x, which measures his waiting time. How many times he waiting for the bus. Of course, because the bus arrives every 5 minutes, his values of x is in this interval. Actually, in practice, we can measure the time only to the nearest unit, such as seconds or minutes. So we do not calculate the actual time. But there is a weakness with this idea, because we have so many errors. So we don't measure the time to the nearest unit, but we find the actual time, so that we don't use the discrete random variable and use or define new approach that is the continuous random variable. If the discrete case is defined on a finite or countable set, the continuous random variable is defined on an uncountable set. That is a set which is not countable. In this lecture, we use interval for uncountable set. So if we have an interval, it is an uncountable set, and the continuous random variable is defined on this uncountable set. And for the previous the specific definition, mathematical definition, the variable random x is continuous if there is a non-negative function f from R to this set such that for any interval like this, the probability of x in this interval is equal to the integral from a to b ft dt. And the little f is called the probability density function of the PDF of x. Yeah, this is the mathematical definition about continuous random variable. Similar with the discrete case, we also have the definition of the cumulative distribution function, or CDF. In continuous case, that is the function big F, which measure the probability of x less than or equal little x. And in this case, we use the integral from negative infinite to x ft dt. And similar with the PMF, there are two requirements for a function to be a PDF. That is, number one, the value of fx is greater than or equal 0, and this integral is equal to 1. Okay, let I illustrated the meaning of the integral. I call that this integral actually measure the area under fx, area of the region under fx above x-axis from x equal to a until to x equal to b. Yeah, this. So in our graphic, if we have f x, the integral measure the area of a region under f above x-axis from x equal to a to x equal to b. So we measure the area of this region, the orange region. With this concept, we illustrate this integral to be the area of origin under the function little f above x-axis from negative infinite to the x. So if we have a function like this, this is the PDF. Yeah, and then I have x in this point. Now the cumulative function at x is represent the area of this region from infinity to x. Yeah, this is the graphical representation of the CDF. Find the area under the curve above x-axis from infinite to x. Yeah, this is the illustration. And for our integral, we can use the general formula. We can use this general formula, that is the integral of fx from a to b is equal to fb minus fa, where fx is the integral of little f, and yeah, we can use this formula, or we call it the fundamental theorem of calculus, to find the value of the integral. Yeah, this is the illustration about the CDF in continuous case. And if f is continuous, then we have this relation between the CDF and PDF. That is, the PDF is the derivative of the CDF. And yeah, directly from the fundamental theorem of calculus, the probability of this interval is this integral. Okay, let me see the example about the PDF and how to find the CDF of this function. Okay, again, we move to the whiteboard. X over 2 and 0, x for this value, this is otherwise. Okay, and then first of all, we want to find the probability of x less than 1. Yeah, before we go to this question, we can clarify that this function is a PDF. It's clear that the value of fx is greater than or equal 0, and then the integral of this is equal to 1. Before we deal with the integral, we draw the graph of the PDF first. From 0 to 2, it follows the line, the orange line, and then yeah, this is 0, this is 2, of course, this is 1, and 0 otherwise means this, for the values greater less than 0 and 0 again for all x greater than 2. Okay, and by our previous illustration, we can find this integral by this. We divide this integral into 3 parts, from infinite to 0, from 0 to 2, and from 2 to infinite. Yeah, because this integral means the area of the region between the curve and the x-axis from mean infinite to infinite. So because the value of fx before x is 0 and also 0 for x greater than 2, we only consider the non-negative area, that is this triangle. So instead using the integral, we can find the area of this region, that is by the formula of the triangle, that is half times the base 2 and the height, that is 1, and we get this region have area equal to 1. And of course, similar with the previous method, if we use the integral, we get this, and it is equal to half times the integral of x is x squared over 2, and we put the upper bound and the lower bound, 2 and 0, and it is equal to half times 2, that is 1. Yeah, it is equal. So so in conclusion, that function is a PDF. Any question about the way to check whether it is a PDF or not? Yeah, just consider the non-negative values. Okay, let's continue to our problem, that is the probability of x less than 1. Okay. 1, yeah, 1 is here, 1, and the probability x less than 1. What is the integral of this value? Integral from
1 to 0.
1 to 0. Yeah, from 0 to 1. And then what is the function?
X divided by 2.
X divided by 2. Okay. And we do the integral. The integral is x squared divided by 2. Put the bound 1 and 0, and then it is equal to a half times, substitute 1, we get a half, substitute 0, we get 0, so it is a quarter. And yeah, the probability of x less than 1 is equal to a quarter. Good.
Sir, I have a question.
Please
So the fx actually reflects the probability. So the fx for x between 2 and 0 is x divided by 2, right? Does that equal the probability?
For the continuous case, the fx is not represent the probability. It is different with the PMF.
So if we want to find the probability of x less than 1, shouldn't we divide the 1/4 by half?
Oh. No one. If we want to find this probability, we for this probability just follow the definition. If from the definition before we get this integral, actually the integral is like this. But because the value of fx from mean infinite to 0 is 0, we only consider this integral. And actually, fx does not represent the probability for the continuous case. In the continuous case, we cannot find the probability of x equal x directly. Because it is impossible because in uncountable set we can find the precise value. For example, if x denotes the amount of water, we cannot find the precise probability. So we use the continuous case, and our hypothesis is we only find the probability of the interval. For example, this we cannot find the probability of x exactly 2, but we can find the probability of x between 1.99 and 2.01. It is possible for PDF, but we cannot find these values directly. That's one.
Okay, sir. I have a follow-up question actually. So what does the fx in this case reflects? Is it just based on the question, the fx one? Like how do you get x divided by 2 if you if the x is between 0 and 2? Is it just based on the question?
Oh. Okay. I think I cannot give you the whole explanation about this. Let me save it for my question, and then I will re-explain to you on the next week. Okay, that's all. But yeah, I'm sorry I cannot completely describe it.
Okay, sir.
Yeah. I'm sorry. I will try to find the meaning of for this function. Yeah. Yeah. Okay. Okay. But it is a good question. Okay, let's continue to the second question. That is the probability x between half and 1.5. half. Yeah, from the properties, it's equal to this integral. Yeah, and it is equal to half times 2.25 divided by 2 minus 1.25 divided by 2. Yeah, you can find the final answer by yourself. And then for the CDF, similar with the PMF, we divide to three area, to three interval. And then from the picture, when x is less than 0, for example, x is here, of course, the CDF is 0. And similar with the case x equal to 0, it is also 0. After that, for the second interval, for example, x is here. This integral represents the area of this triangle. So it is equal to 0x divided by 2 dx. I'm sorry, not x but t. For different variable. T. This is a half 0 x a quarter square. Yeah, and this is the value of cumulative when x is between 0 and 2. Then for the next case, for x equal to 2, it is equal to this integral. Of course, the value is 1. And for the x greater than 2, of course, the cumulative is 1. Yeah. Well, in conclusion, the CDF is a quarter x square for 2, 0 for x less than or equal 0, and then 1 for x greater than or equal 2. Yeah, that is the CDF of this problem. Is there another question for this problem? Okay, great. Thank you for the discussion about this problem. I'm sorry I can answer all of the questions. Let we move to the PPT. Yeah, next that is an exercise for you, and yeah, and we continue to the more complicated problem. I will give you the idea for this function. From 0 to 1, it is a line y equal to x, and from 1 to 1.5, it is just a constant. This is x. Yeah, I will illustrate only two case of x, that is x half and x 3/2. Now for the first value, the cumulative at a half is the integral from mean infinite to a half ft dt. Or if we consider only the non-negative value, it is integral from 0 to a half. Yeah, actually, we want to find this area. So we use the function x t. I'm sorry, t, not x, t gt. So that this integral is equal to a half t square a half 0. That is a half times a quarter 1/8. And for the second cumulative, the function at 3/2 is this this quinarea. I will use this quinarea. Actually, the definition of the function are different in these two intervals. So we must divide our integral. We must divide our computation into two integrals. That is the integral from 0 to 1 t dt plus the integral from 1 to 1.5 1 dt. So it is equal to this, and it is equal to this. Now you can finish the computation by yourself. Yeah, this function is different with the previous one because we have two different definition for two different intervals. Yeah. So you must be careful if we deal with this function because they have different definition based on the interval. Okay, is there a question from you? Okay, yeah, for the complete explanation, you can see in my PPT or in the source book. It is an example in that book. Okay. Okay. To sum up our discussion, we close it with the properties of the CDF. That is, the first property is the value of the fx is between 0 and 1. And then for number 2, the limit of x tends to mean infinite is equal to 0, means if x gets smaller, then the value of fx tends to 0. And for this limit, it means for more bigger the x, more the values of fx is going to 0. And then for the third part, f is not non-decreasing function. That is, for all x1 less than x2, the cumulative at x1 is less than or equal to cumulative at x2. Yeah, and yeah, this is also an exercise for you. And this also. Okay, this is the end of our discussion in continuous random variable. After that, we will continue to the concept of expectation. Okay. Okay. Before we go to the expectation, is there any problem with this slides? And yeah, I will. Oh yeah, I see this example is not usual because the value of x is in this interval. Yeah, for this function, for checking is it a PDF or not, we use the improper integral. Yeah, we have discussed it in our tutorial at last Friday. For the improper integral, if we want to check the second requirement, we will check the integral from 0 to infinite to e minus 2x dx. And by the definition of the improper integral, it is equal to limit t tends infinite integral 0 t to e to the power of minus 2x. And we will solve the integral first. That is limit t tends to infinite. This integral is equal to minus e to the power of minus 2x. The lower bound is 0 and the upper bound is t. Minus e minus 2t plus 1. And of course, from our graphic, the graph of e to the power of minus 2x is this, like this. So this limit when t goes to infinite, of course, the function tends to 0. So the final answer is 1. And yeah, clearly it is a PDF. So if we deal with an interval like this, we have to use the concept of improper integral. Yeah, that's my remark for our example. Then let's continue to the concept of expectation. For a random variable x, we define the expectation of x denoted by this ex, right? For the first one, ex is equal this sigma, the sigma of all x times its probability px for all x with the value of px greater than 0 if x is discrete. And if x is continuous, we use this integral. Yeah. In conclusion, it is important to know whether the variable random is continuous or discrete, because the definition of the expectation are different for discrete and continuous case. For example, if we deal with this experiment of rolling a pair die 6-sided, we get and x is the outcome. X means the outcome. So the possible values of x are 1, 2 until 6. And because this is a fair die, we get the probability of each little x is equal to 1/6 for all x. Then by the definition, because x is a discrete random variable, the expectation is the sigma of x times px from x equal to 1 until 6. That is the summation 1 times 1/6, 2 times 1/6, 3, oh, I'm sorry, 4, and 6. Yeah, it is equal to 7/3. Yeah, and the expectation of this random variable is 7/3. Okay. Yeah, just multiply the little x with its probability for expectation, and sum all of the x with the probability not 0. This is important. And then if we deal with the continuous case, we use integral. Yeah, it is a PDF of random variable x, and because it is continuous, we use this integral of x times fx dx and x from alpha to beta. It is equal with 1/beta minus alpha. After that, because this is a constant, we can move it to in front of the integral. like this, and then solve the integral. The integral of x is this alpha beta. For the integral, substitute beta square divided by 2 minus alpha square divided by 2. Write a half into this place, and we factorize the beta square minus alpha square to beta plus alpha times beta minus alpha. So we simplify our computation to this expression. We cancel beta minus alpha, and we get the expectation is a half times b plus alpha, beta plus alpha. Yeah, this is the expectation of our PDF. Yeah, just use the concept of integral and also the factorization method. Is there any problem in this example? Good. From the definition of expectation, we use only x here. But actually, from this properties, if we have gx as a function of the random variable x, we can find the expectation of gx by this formula. That is, if x is discrete, we use sigma x gx times px, and then if f is continuous, we use integral of gx times fx dx. Just replace x by gx. And then another property is given in this box. If we have c is a constant, and then we have gx, g1x until gnx to be functions of a random variable x, such that the value of this expectation and this expectation exists, then the first property is the expectation of the constant is equal to that constant. Number two, the expectation of c times gx is equal to c times the expectation of gx. Then if we have this sigma, we can spread the sigma into the sigma of the expectations. So the expectation of the sigma is equal to the sigma of its expectation. And with this property, we can prove this special case of the function gx, that is the gx is equal to ax plus b. Okay, let's see the proof. For the first case, if x is discrete, then we use the sigma, right, for the expectation. And from the previous theorem, the expectation of this function is equal to the sigma of all x, ax plus b times bx. We use distributive law, so we get ax times bx plus b bx. After that, from the properties of the sigma, we can spread our sigma into these two sigma ax times bx plus sigma bpx. So that since a and b are constant, we can write this sigma into a times sigma x times bx, and this with b times sigma px. After that, we call that the expectation of discrete case is equal to this formula. So we can write the sigma into the expectation of x, and then because px is an PMF, we get the sigma of all x is 1. So we get this is b, and we have done our explanation about the theorem in discrete case. And for the second case is this the continuous. If we deal with the continuous case, we use integral for this. If x is continuous, then the the expectation is this the integral of ax plus b times use distributive law again. The fx. We will use fx for the continuous case. So, fx. So use the property of integral a times x. Yeah, because it is continuous case, this is equal to the expectation of x plus b, since this values is 1, since f is unbidden, so the integral is equal to 1. Yeah, and we have completed the proof of the continuous case, and clearly this theorem is true for every random variable. We can use this expectation to find another expectation with the condition we know the value of ex, such as we know the value of ex is equal to this value, and then if we are asked to compute the expectation of new random variable, for example 2x plus 1, you can use this theorem. So just compute 2 times expectation x plus 1. It is 2 times 7 divided by 2 plus 1, and it is equal 8. Yeah, we can compute another expectation by this formula, as long as we know the quantity of ex. Yeah, it is just a tool to help us compute another expectation. And of course, we can use all of these properties to compute another expectation. Okay, let's discuss the spatial expectation, that is the moment, the k moment. It's just a particular case of of this theorem. I mean, for gx equal to x to the power of n, or k, I am sorry, for x to the power of k, the expectation is sigma x to the power of k times px for x, for a random a discrete random variable, and then for the continuous case, that is the integral x to the power of k times fx. This is the definition about k moment. K is a natural number, and if k is, of course, if k is 1, the first moment is actually the expectation. Okay, just follow the pattern for the value of k. For example, in the previous example, we have found the expectation, and then now we will compute the second moment. By the definition, what is the expression of the second moment? Could someone give the definition? Is it discrete or continuous?
Discrete.
Discrete. Okay, if it is discrete, we use sigma. After that, what is the expression? Use discrete x squared sigma
X squared times the probability.
times the probability. And what are the value of x? We have x from 1 until 6.
Yeah, so for example, like 1 times 1 divided by 6, and then 4 times 1 divided by 6, and then 9 times 1 divided by 6, and then go on.
Right. Actually, we complete the sigma first. X from 1 until 6, like this. And then, as you mentioned before, 1 square times the probability, 2 square times the probability, 3 square times the probability, and 4 square, 5 square, 6 square. And you can compute these values. Yes. Yeah, it is important to determine whether x is continuous or discrete. Okay, for the continuous case represented in this example. Okay, maybe I will give you a few minutes to find this second moment, please. Let's Okay, what is the expression of the second moment? The second moment is ex squared. Ex squared. Is it continuous or discrete?
Continuous.
Continuous. Okay. For continuous case, what's the expression in the curve? Integral from integral x squared times the function value, that is this. After that, could you continue it? What is the on?
From A to B.
From alpha to beta, right?
Oh yeah.
Okay, and then what is the next step?
And then you just convert the x squared into x, x cubed, and then divided by 3.
3. Yeah, yeah. So before that, we write this one, right? And then x cubed over 3, right? But and then this is equal to 1 over 3. Sorry. Beta cube over 3 a over cube 3, and then this is equal to 1 at 2. Yeah, actually, yeah, this is the can we simplify it? Beta cube minus alpha cube. Can we spread or factorize it? Beta cube determine alpha beta square alpha square. Yeah. We can factorize this expression into these two multiplication. So it is yeah. So the final expression, the simplest expression is this. Okay. Yeah, and this is the second moment of this video. Yeah. Oh yeah. This is the last slide for the second moment. Yeah. Just follow the definition for the K moment. Is there any question from you, please? Okay. Okay, great. I hope you can receive the idea of the K moment and the expectation. So for the next, we deal with the concept of variance. That is the value of expectation of x minus ex squared. We put this bracket after that, square the value of x minus ex, and to find the variance from the second moment and expectation, we put mu as the expectation, and then we use the properties of expectation. That is, from the definition, for x is equal to this expression. After that, we squared x minus mu, we get x squared minus 2x mu plus mu squared. After that, by the property of the expectation that spread sigma, we can write ex square minus 2 mu square plus mu square. Simplify it, we get negative mu square. After that, convert mu to ex, we get the variance of x is equal to the second moment minus the expectation squared, like that. Yeah. So we have another expression about variation. And for the previous example, when we roll a Faraday and x denotes the outcome, we get the expectation is 7 divided by 2, and from the computation, the second moment is 91 divided by 6, and from the previous formula for variance, the variance is equal to this expression, and the value is 35 divided by 12. And again, the variance also have some properties. The property 1 we had proven in the previous slide, and for the second property, that is the variance of ax is equal to a square times variance x, where we get this formula. Okay, let we compute ax, and from the number 1 we get it is equal to the expectation of ax squared minus the expectation of ax squared. The first term, it is equal to a squared times x squared minus from the previous property of expectation, we get it is equal to a times ax plus b. Because in this term, the value of b is equal to 0, we get this expression is equal to a times ex. After that, square them. Okay, again from the previous property, it is equal to a square times ex squared minus a square times the expectation square. Move factorize a square, we get this. And finally, we get a square is equal to variance of ax is equal to a square times variance of x. Yeah, this is the explanation about the second property. Yeah. For the proof, yeah, maybe it is not easy for you, but yeah, I try to deliver it for you, so you can maybe at least receive or capture the idea at first. Okay. Yeah, this is the end of our discussion about expectation and variance. Before we go to the next tutorial, is there any question from you? Okay. Okay. For the next is the special random variables. In this lecture, we only consider some of them. That is, for the discrete case, there are uniform, binomial, Poisson, and geometric. And then for the continuous case, we have uniform in the sense of continuous, and then exponential, and also the normal. Yeah, and today I will only give a brief introduction about the definition, and for the next meeting we will deal about its expectation, its variance, and we learn about the MGF or moment generating function of these special random variables. So today we only learn about the basic definition. Okay, and for the first one, the uniform in discrete case, the example of this probability distribution is the random variable x, which shows the outcome when we roll a fire die. As we seen before, the probability of all x are equal. That is 1 divided by 6, equal for all values of little x. Now, because the probability are the same, we call it the uniform probability distribution. And for the precise definition of the uniform discrete, that is in this box, a random variable x, which has values x1, x2 until xn, is said to have uniform probability distribution with parameter n, and we denoted it by un if the PMF, it is the PMF, right? The PMF is in this form. That is, the value of Px is equal to 1 divided by n for all x from x1 until xn, uniform. Because it is PMF, we can check that the sigma of Px from Pxi from I1 to 6 is equal to the sigma from 1 to 6, 1 divided by n. Oh, I'm sorry, not 6. It is n. And the sigma is equal to n times 1 divided by n. And it is equal to 1. So our requirement is fulfilled, and of course this function is a PMF. This is for the uniform random variable which has PMF formula like this. And then for the second distribution, that is the binomial, we start with the definition about a binomial experiment. That is an experiment which follows these properties. For the number one, the experiment consists of n trials, and they are identical. For the simple case or simple example about binomial is experiment tossing a coin n times. We have a coin and then toss it n times. Identical means the condition of every tossing are same. And then for each trial, we have only two outcomes and one must be occur. That we call the success and the failure. And then the probability of success of each trial is P, and same for every trial. And then, of course, the probability of the failure is 1 minus P. And then we assume that the outcomes of the trials are independent. That means if the first toss shows head, it does not influence the second toss. And then the last assumption that is we define the random variable x as the number of success in the n trials. Okay, this is the definition of the binomial experiment. Okay, this is the definition about the binomial experiment, and start with the definition of the binomial random variable. And I call again the number of ways of obtaining x success in n trials is this n combination n x. And yeah, and then we must check that these two conditions are hold. And yeah, this is the exact definition about the random variable which have binomial probability with parameter n and p if its PMF is given by this formula. That is, the probability of x equal little x is combination nx p to the power of x times 1 minus p to the power of n minus x. As we see, x means success, and the probability of success is p. It means this notation means we have x success, and then of course because the tossing are independent, the probability to have x success is p to the power of x, and the probability to get failure is 1 minus p to the power of n minus x. Because if we have x success, of course we have n minus x failure. And then you can check that the sum of all px equal to little x from x to 0 to n is equal to 1. For the explanation, you can refer the book written by Ross, the introduction to probability model, to find the reason why the sigma is equal to 1. And clearly it is a PMF for the binomial case. As I mentioned before, the experiment of tossing 5 coins is the example of binomial. For example, we have 4 coins and we flip all of them, and then the outcomes are assumed independent, and we will determine the probability that a head and 3 tails are obtained. Because this experiment is a binomial experiment, we can use the the binomial distribution by define x to be the number of head or success, and then because the coin are fair, the probability to get head is equal to a half, and also 1 minus p is also a half, and then there are 4 trials, so n is equal to 4, and the random variable has parameters 4, comma a half. So if the question is the probability that a head appears, it is equal to the probability of x equal to 1, and from the previous definition, it is equal to the combination for C1 times a half to the power of 1 times a half to the power of 3. Yeah, this is the probability of one head appears. Yeah, and then if we want to determine the probability that at most 2 heads are obtained, we can write it in this notation, and of course the probability is the sum of these 3 probability. Yeah, for example, for x, for this middle term, this for C, I mean for this, for C2, half to the power of 2 times a half to the power of 2. Yeah, and you can and you can compute the final answer. This is also one of the example about a binomial. And for the Poisson, a discrete random variable is said to follow the Poisson probability distribution with parameter lambda, denoted by this poi lambda if the PMF is in this form. And once again, you can refer to the Ross book to find why we have the sigma of px is equal to 1. And then for the last type in discrete is the geometric probability distribution. It accommodates the experiment of this. Suppose that there are n independent trials with 2 possible outcomes, that success and failed, and then the probability of success is p, and let x be the number of trials required until the first success happen. Yeah, for this random variable, you can refer to the very early example, that is our experiment of tossing 2 coins until we get a head. This random variable is called the geometric random variable, and the PMF is given by this formula. Fn, or the probability of x equal to n, is 1 minus p to the power of n minus 1. N minus 1, n minus 1 is the number of failed and of course, because we have 1 success, so we multiply this expression with p, and n from 1 to 3 and so on. Yeah, by this geometric explanation for our previous example, we can define the PMF of this random variable. And if our random variable is like this, from the it is geometric, so our probability of x equal to n is I mean since the coin fair, since the coin is fair, we just only use a coin here. The probability of success is p, and then the probability of fail is also a half. They are same. So our definition is like this. P a half to the power of n minus 1 times a half. That is a half to the power of n. Yeah. This is the PMF of our previous example of tossing coins and tossing a coin until we get a head. Yeah, this is the explanation. And then we move to the second type, that is the continuous case. For the first special random variable, that is the uniform in the sense of continuous, that is a random variable which has PDF like this formula. Yeah, in the previous slides we have discussed about the expectation and also the second moment of this PDF, right? Uniform, the fx is equal to 1 divided by beta minus alpha for all x between alpha and beta, and 0 otherwise. And we can check this integral is equal to 1. So it is a PDF. And then you can also check that the CDF of the uniform random variable is this. And then the second one is the exponential random variable, that is a random variable which has PDF in this form. And we must use lambda greater than 0. This is the exponential, and if we check this integral, this improper integral is equal to 1. So clearly it is a PDF. And then you can find the CDF as an exercise. And our last distribution is the normal form or normal random variable, that is a random variable with parameters mu and sigma square, or the mean and the variance, if its PDF is given by this formula. And, yeah, this is a complex function, right, for the normal random variable. Yeah. Okay, it's just an introduction about the special random variables, and for the next meeting we will see what is their expectation, what of variance, and then the concept of moment generating function. Yeah, that's all of our meeting today. It is the last slide, and we have finished our material. Is there any question from you from our first slide until this slide? That's oh, no questions. Okay, great. Okay. If there is no question, I think we can finish our class. Thank you very much for your attention. I'm sorry I cannot give explanation or the answer of one question from Owen. I will find the answer. And yeah, thank you. See you on the next week. Bye. Good evening or have a
Thank you,
nice
sir.
day. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.